Now that we've spent all of this time with radicals, we can talk about kind of the importance of them appearing and stuff we've even done earlier. So we're going to start with complex numbers, and then in our next section, we're going to talk about solving quadratic equations. And so we're going to go through first what is the imaginary unit, and then how does that relate to what a complex number is. And so what we've seen before is we've gone through and we've solved equations like x squared minus 4 equals 0. We spent a ton of time factoring. We spent a ton of time trying to find techniques to solve those things. But if we were dealing with something like x squared equaling negative 1, there is not a real number that will solve that equation. And the reason is if you take a positive number and times it by a positive number, you get a positive number. If I take a negative number and times it by itself to get something squared, it also gives you something positive. So there's no way a real number times itself will ever give you anything negative. Now, that being said, these kind of equations do still pop up. And so what we ended up creating is the imaginary unit to help us solve these equations. And so the way we defined it is I is going to represent this imaginary number. And so I squared is going to equal negative 1. It will solve that equation of a number times itself equaling a negative. And the way you can actually think about just the imaginary unit then is if you take a square root of each, I is going to equal the square root of negative 1. So anytime we see a negative value underneath a radical, we immediately know it's an imaginary number. So let's get some practice. Let's try to figure out how we can simplify a bunch of these expressions that all have minus signs underneath the radicals. And so we know none of these are real numbers, but they're going to relate to imaginary numbers. And one of them might actually end up being real. So for this first one, we're going to take it the long way, but then afterwards we'll go through and we'll do a shortcut. So the way you can think about the square root of negative 4, I know that's definitely not real. We've been saying we can't take square roots of negative numbers. But I can write that as negative 1 times 4. And then using our properties of radicals, we can go ahead and take the square root of each of these. And then this piece, the square root of negative 1, is exactly what we're defining to be this imaginary unit I. And then the square root of 4, we can actually work with. It's 2. So the way we can actually simplify this is the square root of negative 4 is equal to 2i. So what we can actually always do to kind of make our process a little bit simpler is instead, as soon as you see this minus sign, immediately pop out an I. And then you're going to go ahead and work with that square root as normal. So the square root of 4 gives us 2, and then the I is attached because we had that minus sign under the radical. So let's try that for this next one. Immediately I have this minus sign, so the thing I want to do is I want to get rid of the minus sign, and I want to pop out an I. And then working with that square root that's left over, the square root of 36 is 6. And that minus sign is just staying out front the entire time. So this ends up simplifying to minus 6i. In this next one, same thing. Immediately, I see that minus sign underneath, so make it positive and put an I with it. And then we want to go ahead and we want to simplify this radical as we would. So 18 we can write as 9 times 2, and 9 is a perfect square. And then the I is attached. And then when you take the square root of 9, it gives us 3. So the square root of 18 simplifies to 3 root 2. And then we have an I attached to it. Okay. For these next couple ones, I cannot stress enough how important it is that immediately when you see this minus sign underneath, you take it out and you write it as I. So for this one, before I work through simplifying these radicals, I immediately want to make that positive square root of 10. We're going to attach the square root of 2, and the I is going to pop out at the end. Okay? And now I'm going to go ahead and combine these two because they're the same type of radical. It gives us the square root of 20, I. And then 20 we can simplify. It's 4 times 5. And then 4 is a perfect square, so this is 2 root 5, I. Okay. Now in this one, it's not a super big deal if you went and multiplied the 2 and negative 10 first. But for this next one, it would end up giving you something wrong. So we have the minus signs underneath the radical, and it's underneath both of them. So each of those radicals is going to pop out an I. So we get I root 7 for the first one and I root 2 for the second one. And then from here, I times I, you do exactly what you did before. X times x is x squared. I times I is I squared. And then with the radicals, square root of 7 times square root of 2 gives us the square root of 14. And now here, the thing is, you always want either just a nice number or something times I. And I squared, we know what that equals. It's really negative 1. So we get negative 1 times the square root of 14, which is just negative square root of 14. Okay. So if you tried to go ahead and multiply what's underneath first, you cannot do that. Because what happens is you'd have negative 7 times negative 2, which would give you the positive square root of 14. So you end up with two completely different answers if you don't take the I out first. So always make sure you do that. Okay. So this leads into our concept of complex numbers. And this is basically when we're going to have something that involves this imaginary component, but we can add a real number to it. So a complex number is of this form, a plus bi, where these numbers a and b are real numbers. So they can be 5, they can be negative 7, they can be negative 2.9, they can be the number pi, they can be radicals as well. So they just have to be real numbers in front. This piece that's completely by itself, so it's not attached to the I, is called the real part of the complex number. And then the part that is attached to the I is called the imaginary part. So it's really two different parts that form this complex numbers. So when I'm working with combining them, you can only add or subtract or deal with the components that are alike. So I can only add the real parts together. I can only add the complex parts together, and vice versa. So let's just try a ton of examples. We want to do whatever operation we're told, and we want to simplify the complex number. So starting with this one, we have one complex number plus another. Really, I don't need any of these parentheses here, so you can just write it out completely as 3 plus 2i, and then it's minus 4 plus 5i. So I want to look at the pieces that are alike. I have 3 minus 4, so I can combine those to negative 1. And then I have my imaginary part, which is positive 2i plus 5i. Those combine to positive 7i. And that is our simplified complex number. For this next one, I want to go ahead and I want to distribute that minus sign to each thing first. So this is 5 minus I. When I distribute that minus, it turns it to positive 1 minus 4i. And again, combine the like parts. So 5 plus 1 gives us 6. And then negative I minus 4i gives us minus 5i. Now, when we deal with multiplication, we're not going to worry so much about division in this class, but if you're going on to college algebra, you'll talk about it there. When we're dealing with multiplication, we can go ahead and just multiply. And again, the only things that we can really combine or actually multiply out are the like pieces. So what we're really doing in this one is we have 3i times 27i. So the 3 and the 27, we can multiply together. So if you do that, it would give you 81. And then we can take I and times it by I. That would give us I squared. And again, this isn't fully simplified because I know what I squared is equal to. I squared is -1. So really these two things multiplied to give us -81. So we just got two more examples. And again, more multiplication. For this first one, we're going to take 5i and times it by this binomial. So again, want to distribute this 5i. So this gives us -6 times 5i plus 2i times 5i. And so again, I only multiply the like pieces. -6 times 5 is -30i. 2 times 5 is 10, and then I times I gives us I squared. And again, I squared is -1, so this really gives us -30i minus 10. Now really this form isn't quite appropriate. We usually like to put the real part first. So we'll put that minus 10 first and then minus 30i at the end. So this form is called standard form for a complex number. And that's typically how we want our answers to always be displayed. The real part first, the imaginary part second, and we should only have one real, one imaginary part. Should have no I squareds, no i's to other powers, just a number and then possibly a number times I. So we got one more, and it is a binomial. So we're going to go ahead and apply our foiling just as we've done before. So our first piece gives us 4 times 1. The outer is 4 times -2i. The inner is 3i times 1. And then the last is 3i times -2i. So we have a lot of simplification that we have to do. 4 times 1 is just 4. And then here, 4 times -2 is -8i. 3i times 1 is 3. And then 3 times 2 is -6. But we have I times I, so that gives us I squared. So we can do some combining. So here we have -8i plus 3i. That gives us -5i. And then again, I never want to have an I squared. I squared is -1. So this is 4 minus 5i, and that ends up turning into a plus 6. And then again, I'm still not fully simplified because there's some stuff I can combine. The 4 and the 6 combine to give us a 10, and then a minus 5i. And so that is in standard form.